Welcome back. This is video lecture 3.1, our first video lecture in chapter 3. What is the corresponding reading in our textbook, Fundamentals of Physics? It's chapter 3, section 1, Vectors and their Components. And I will emphasize from the beginning that this chapter in our book is probably the most important chapter in the entire book. Because as we will learn, many physical quantities that we deal with in the study of the physical world are what are called vector quantities. Therefore, we must learn the proper mathematics for dealing with vector quantities. How do you do mathematical operations like addition or subtraction or multiplication with vector quantities? We must learn how to do that correctly because there are many vector quantities in nature. And we will be working with vectors throughout the rest of the book. Okay, so this chapter is well worth an investment of study time and effort, and it will pay off big later on. Okay, so let's begin our summary of chapter 3, section 1. Let's start with a few definitions. To a mathematician or a physicist or an engineer, quantities in nature are conveniently categorized. And the two of the categories we're going to be talking about are scalars and vectors. Let's start with a scalar. A scalar is any quantity that's described by a numerical value without an associated direction. Okay? It's just a number, and there's no directional aspect to it whatsoever. Let's name some examples of scalar quantities from physics, from nature, that we've come across already. You might want to pause the video and think about a few for yourself and then come back. Okay, did you think of some scalar quantities? Quantities that would be described by a numerical value with a unit on it, most likely, but aren't associated with any particular direction. So here's an example of a scalar quantity. Time. I may have a clock or a timer that's running, that was started at some time and has been running, and there may be a moment when I stop it and I ask, what does it read? What is the time on the timer? And maybe it reads 75 seconds, but it's just a number with a unit, 75 seconds. We certainly wouldn't say, well, the time is 75 seconds to the right. There is no directional aspect in that simple everyday sense of left, right, up, down, okay, to time. Maybe you thought of some other scalar quantities, like one that we mentioned, or was mentioned in the video lecture for chapter 1, mass. A measure, if you like, of the amount of material of a substance. SI unit kilogram, also sometimes measured in the unit of gram. You can measure the mass of an object, usually on some kind of a pan balance. Like you could measure the mass of this pencil on a pan balance. And maybe you would get that the mass is 25.3 grams. But it's just a number with a unit. There's no direction, right? It's not 25.3 grams down or up or left or right. There is no directional aspect to mass. It is a scalar. Here's another scalar quantity that maybe you thought of. Temperature. Right? You could measure the temperature of a glass of water. And maybe you discover that it's 15 degrees Celsius. It's not 15 degrees Celsius down or left or right or up, right? So it's just a number with a unit but no direction. That's a scalar quantity. Scalars are the numbers you're more used to when you first learn to add numbers in, say, 3rd grade. Or actually 1st grade, I guess, right? It was scalar addition. How do you add two scalar numbers that you were taught? Right? The first kind of addition and subtraction, or multiplication you were taught was for scalars. But if you study the physical world much, you come across another kind of quantity called a vector quantity. And that's a quantity that has both a size, which we call its magnitude, and a direction associated with it. Let's see if we can name some examples of vector quantities. I'm going to let you think about it. Pause the video. Think if you can of some vector quantities. I'll give you a hint. We came across some in Chapter 2 when we studied kinematics along a line. So pause the video, think of a few vector quantities, and come back. Okay, welcome back. So, do you remember some of the vector quantities from Chapter 2 when we studied kinematics along a line? For example, displacement, right? Change in position. That was a vector quantity. It had a magnitude and a direction. If the particle is moving along, say, an x-axis, that's, say, horizontal, if the particle ends up, from my perspective, to the right of where it started, that's a positive displacement. If it ends up to the left of the place where it started, that's a negative displacement. Positive is in the plus x, negative is in the negative x direction. There's a directional aspect to displacement. So it has both a magnitude and a direction. Another vector quantity we studied in Chapter 2. How about velocity? It has a magnitude in meters per second and a direction, plus x or negative x. The direction is telling you the direction in which the particle is moving. A third vector quantity we studied in Chapter 2, acceleration, with a magnitude in meters per second squared and a direction, plus x or negative x. Okay. All right, so scalars are quantities represented by a number with units, but they don't have any directional aspect. And vectors have a size, a magnitude, and a direction. Okay, now let me introduce what we're going to do next with a little bit of explanation. So we did have vector quantities in Chapter 2. We've just listed 3 of them when we studied kinematics along a line: displacement, velocity, acceleration. But to represent the directional nature of those vectors for motion along just a line, say an x-axis, was easy because there were only 2 options. The vector's direction could be plus x or negative x, if you like, right or left. Or maybe if you were using a y-axis that went up and down, the directions were plus y, up, or negative y, down. But the point is, only 2 directions are possible. Well, not all motion is along just a line. Imagine a pool ball hit on a pool table, moving around on that flat, felt pool table. That's what we would call 2-dimensional motion. And you would need 2 axes, an x and a y, to describe that motion. And what about dealing with vectors when you have 2-dimensional motion, with both an x and a y axis? Things get a little more complicated, and talking about the direction of a vector in 2 dimensions is mathematically more complex than it is in 1 dimension. And that's why we have to really pause in our study of kinematics and insert an entire chapter, this chapter, Chapter 3, to talk about how to deal correctly with vectors. So let me start getting used to how we represent vectors in physics. Okay, there are a number of different ways to represent vectors. Okay? All right, so what you see now in the middle of this screen is a top-down view of an XY coordinate system. And maybe, let's say, there's a particle moving around in this XY plane. And let's say that it started at a point in the XY plane that's right there. And maybe it moved around in some complicated way, but ended up at that point right there. So the 2 dots represent the 1 particle at 2 different times. I have drawn an arrow there. And that arrow represents a vector quantity. To be specific, in this case, that arrow represents the displacement of our particle from the initial point to the final point. Okay? So a graphical representation of a vector is an arrow, which seems pretty natural if you're going to talk about things that have direction associated with them, okay? Because arrows point. Okay? So the displacement vector for our little pretend particle here, as you can see, points up and to the right in the xy plane because it points from the starting location to the ending location directly, even though the actual path of the particle may be windy and complicated. The displacement vector just points from the starting point location to the ending location. And so it's pretty natural to use an arrow to represent the vector. That's what I call a graphical representation. It's a picture, an arrow. We also have symbolic representations of vectors. A symbol is a letter, for example. And the symbolic representation of a vector is any letter you want, any letter in the Roman alphabet, our alphabet, possibly even the Greek alphabet, okay, with an arrow on top. I use the symbol A here for this vector quantity, so I'll do A, arrow on top. And you can see that's what I've got written there, maybe small, okay, so a little bit too small for you to see. That's what I call a symbolic representation of the vector. A letter, and it would be an italicized letter technically, with an arrow on top. And I want to emphasize how important it is to draw that arrow on top in the symbolic representation of a vector. That's the way you tell your reader very clearly that this symbol A is a representation of a vector quantity with a magnitude and a direction. All right, now, sometimes when you're dealing with a vector, you may only be interested in one part or another of it, its magnitude or its direction, but maybe not both. Okay? So we need to be able to refer to the subparts of a vector, the magnitude only part or the direction only part. Okay? So let's talk about how you represent magnitude. The magnitude of a vector, here's one way to denote it. It's not the only way. You take the vector symbol, in this case the A with the arrow on top, and you put absolute value symbols about it. So if I went back to my symbol A, arrow, and put absolute value symbols on it like that, now I'm telling my reader, oh no, I'm only talking about the magnitude part of the vector. And of course, in our graphical representation with the arrow, the magnitude part of the vector is just how long it is, just its length, without worrying about it, what direction it points in. Okay? So when we talk about a magnitude of a vector, we're talking about the length of its associated arrow. Notice there's no such thing as an arrow with a negative length. You can technically have an arrow with 0 length. It's a bit of a mathematical technicality, but if you think about it for a while, you have to allow for a vector of 0. But there is no vector with a negative magnitude. That would be analogous to drawing an arrow with negative length, and there is no such thing. Okay? Okay. So watch out for that. If you're talking about the magnitude of a vector, then it can't be a negative value. Here's a little tip to get used to. I like to represent the magnitude of a vector as the vector symbol with absolute value signs on it, but most books don't do that. It's too much work. So you're going to need to be aware of the shortcut notation for the magnitude of a vector. It's just the italic symbol with no other adornment. No arrow on top, no absolute values. So for example, with my symbolic representation A arrow for this displacement vector, if I were using the way the textbooks would denote magnitude, I would just draw an italic A, like you see right there. Okay? So, just drawing the italic symbol without any other adornment is the way books will represent the magnitude of a vector. Now don't forget, there's also the directional part of a vector. Again, with the graphical representation of the arrow, it's natural to talk about direction because you just look and see what direction the arrow points in. But we've got to be more specific than just the direction the arrow points in. We've got to have a way to put a number to that. So here's what we're going to do to get direction. At least this is one way to do it. This is the most common way we'll do it. We take the arrow that represents the vector, like the A there, in our slide, I'll draw a little dashed line pointing to the right. That's the plus x direction. And then I measure the angle from there. I'll call it theta. That's an angle in degrees, for example. Or in the SI unit of angle, the radian. But it's an angle of some size, measured from the plus x axis. In this case, I have to go what's called counterclockwise from plus x to denote that angle. Okay, so we're going to denote the angle by giving the direction, of a vector by giving you an angle measured from plus x. We're usually going to use the symbol theta for the angle. Okay, so there's the first few comments about vector quantities in 2 dimensions. Okay? All right, now, I mentioned that when you first learned how to add numbers, I guess probably in first grade, you learned how to add scalars. You learned scalar addition. Well, if that's the simplest addition there is, so of course they're going to teach that to you first. But now we have a new kind of mathematical quantity called a vector. What if we have 2 of those 2 vectors representing the same kind of quantity? Say 2 displacements. Can't we add those 2 vectors to get a net or total displacement? You bet we can. You can always add 2 vectors if they're like vectors. They're both displacements or both velocities. Okay? You can't add 2 unlike vectors, like you can't add a displacement to a velocity. But you can add 2 vectors that are of like quantity, such as 2 displacements. What is the mathematical method for adding 2 or more vectors? I'm first going to show you a graphical method, and then in the later video we'll learn the analytical method that we'll use the most. Okay, here's the graphical method of adding vectors. It's called, one in some books, the head-to-tail method. So let me explain how it's done. It's really quite simple. These drawings show a number of vectors. We really don't care what they are right now, but we're going to add them. The first vector is labeled A, and is right here. You can see it points up and to the right, if you like. And its symbol expression is A with an arrow. Then there's another vector labeled, there's another arrow there representing that second vector, labeled with the letter B and the arrow on top, B arrow. And these 2 arrows, these 2 vectors, have been drawn in what I call head-to-tail configuration. That means that the head of one vector is drawn up to the tail of the other. Look right there in the red circle. The head of A, where the point is drawn up against the tail of B. That's called head to tail. So in the head to tail method of adding vectors, you first draw the vectors in head to tail method. You are allowed, by the way, let's point something out here, to take any vector that you're given, represented by an arrow graphically. You are allowed to slide that arrow around on your 2-dimensional surface, however is convenient, as long as you don't change the length of the arrow or the angle of its tilt. Okay? That's a very handy property of vectors as represented by arrows. You can slide an arrow around wherever you want on the XY plane, as long as you don't change the length of the arrow or you can't change its tilt. Okay? So A and B have been slid around, reconfigured, so that they are in head-to-tail configuration. Then I want to add A and B. We'll call the result S arrow for sum, S-U-M. In the head-to-tail method of adding vectors, the sum of A and B points from the head of A, from the tail of A to the head of B. From the tail of A to the head of the head of B. Or, to say it slightly differently, from the tail of the first vector to the head of the second. So that third arrow there, that is labeled S arrow, is the sum of A and B. and it's got a particular magnitude and direction. That's the graphical method for adding vectors. You need to be able to draw a diagram like that. Okay? If we give you two vectors, you ought to be able to at least sketch what you get when you add them. Here's the nice thing about vector addition. If you have two vectors to add, you can add them in either order and you'll get the same result. For example, there's A followed by B, right? The tail of B is at the head of A. You add them, you get A plus B. It's just the same diagram I had right above. But now let's reverse the order. Let's draw B first, then A. All you got to do is take the B vector right here and slide it down to this location. Like that. And then slide the A vector down to this location, like that. Then we have the head of B at the tail of A. So B's first, then A. But still the rule is that the sum goes from the tail of the first to the head of the second. So we go from the tail of B to the head of A. But it's the same vector as we had when we did A plus B, right? It's the same vector right there in the middle. Right there. Okay? So whether you do A plus B or B plus A, you get the same result. Okay. So far, so good, hopefully. Here's a nice thing about the head-to-tail method. It's easily generalized to adding more than two vectors. Let's say I've got the two vectors A and B, and I want to add to them a third vector, C. So I want S vector that I get when I add A vector to B vector to C vector. Okay? All right, let me draw for you. And let's just say the C vector, I'll draw it over here, goes straight down and is that long. Okay? All right. Well, I'll make my own sketch. It doesn't have to be exactly right. I just want to get the idea across. The vector A goes up and to the right, about that long, from the starting point. The vector B goes down and to the right, like so. Now I have to draw the vector C next, and it has to be head to tail with B. Okay? And I'll just imagine sliding the C that I've already drawn over here over so that the tail of C is at the head of B. Like that. All right? Note then that B and C are head to tail, and A and B are head to tail. So it's just one after the other, like a sequence. And now the rule for getting the sum graphically is you go from the tail of the first, in this case, to the head of the third one, the last one, like that. That's S arrow. From the tail of the first to the head of the last. This way you could add any number of vectors graphically. 3, 4, 5, however many. Okay? Just put them successively, one after the other, head to tail, and it really doesn't matter what order you put them in, just make sure they are one after the other, head to tail. Then draw an arrow from the tail of the first to the head of the last. And that's the graphical method of adding vectors. Now, mathematically, the inverse operation to addition is subtraction. So if you can add vectors, why can't you subtract them? And you can, and we may need to do that. So let's talk about how you do that graphically. I describe the graphical subtraction of vectors as really the graphical vector addition with a little twist. Okay? All right, let's take those same two vectors, A and B, that we had on the previous slide, and let's now take A minus B. Okay. Here. take A minus B. Let's do that. We'll get the difference, I'll call it D, right here. D vector is A vector, whoops, it's a little too high, sorry. There we go. D vector is A vector minus B vector. But all we really want to do is, or what we're going to do, is take A vector plus the vector negative B. So it's really addition. We're going to add A to negative B. So we just got to be clear what vector negative B means. So here I have drawn A and B. Same A and B as before. There they are, right there. Okay? Once you know what B is, it's easy to draw negative B. Because negative B has the same magnitude as B, but exactly the opposite direction. You can see negative B is right here. Same length as B, but exactly the opposite direction. To find the difference, A minus B, look at the picture below, I'm going to take the vector A and add it to the vector negative B, using the head to tail arrangement. So draw A first, and then in head to tail with that, draw the vector negative B. Right? These two are head to tail. And I'm really just adding A and negative B. So the resultant goes from the tail of the first to the head of the last, or the head of the second. And we have now subtracted. We've done A minus B. Although what we've really done is A plus negative B. Here's a little practice for you to do. Let's draw the sum again on the same image. It's the same one we had on the previous slide. In other words, what's A plus B look like? Now think about that for a minute. Feel free to pause the video. What would the vector S, which is A plus B, look like? Okay, well, there's A. B is just exactly the same length as negative B, but opposite direction. So the B, which we've actually already drawn, looks like that. And then the sum S, not the difference, D, goes from the tail of A, to the head of B. So there's S, the sum A plus B. And over on the left is D, A minus B. And the vector S and the vector D are different. They may have the same length in this case, S and D, but they do not point in the same direction. And therefore they are different vectors. So that's the graphical method for subtracting vectors. We need to be able to make these kinds of sketches with arrows and adding vectors and subtracting them. Okay, there's one more important idea in this video that was from this section, Chapter 3, Section 1 in the book, and it's called Finding the Components of a Vector. Very important for the work we're going to do throughout the rest of the book. And what I really ought to say is what are called the scalar components of the vector. But before I talk about how to do that, I need to do a brief review of something from high school, trigonometry. Because we need that when we work with vectors. Okay? Okay. Okay. So here I have on this slide just a trigonometry review. I'm not going to do any great detailed review of trigonometry. That's from high school. Okay? I'm just going to review, but we're going to use trigonometry all the time. So you must know everything on this slide and be very familiar with it. Okay? All right. So this is sometimes called right triangle trigonometry because it's based upon the geometry of a right triangle. So I've drawn a right triangle here on the slide. You can see the right angle symbol right there. And there's a leg with length A, and another leg with length B, and then the hypotenuse with length C. I've also marked the two acute angles, angles less than 90 degrees in the right triangle. I've labeled them theta and phi. Okay? All right. Let me now remind you of the definitions of the three key trig functions. Okay? They are the three key trig functions we're going to use are cosine, sine, and tangent. Remember those? We're going to use them. Let's focus on the angle theta down in the lower left. Here are the definitions of the three trig functions. Cosine theta, sine theta, and tangent theta. Cosine theta, by definition, is, for this right triangle, the length of the side adjacent to theta divided by the length of the hypotenuse. Adjacent over hypotenuse. In this case, it's the length A over the length C. Sine theta, by definition, is the length of the side opposite to theta over the length of the hypotenuse, which means the length B divided by the length C. Tangent theta, by definition, is sine theta divided by cosine theta. Now, if you take the expressions for cosine theta and sine theta, A over C and B over C, and you do sine theta divided by cosine theta, you just end up with the expression B over A. Note that B is the length opposite to the angle theta, and A is the length adjacent to the angle theta. So you'll often hear people say that tan theta is opposite over adjacent. What tan theta really is sine theta divided by cosine theta, and that happens to come out to be equivalent to opposite over adjacent. Now you could also take the angle in this upper right corner of the triangle. That's also an acute angle. I've labeled it there with the Greek letter phi, like that. Theta, which was down here, looks like that. Those are the two most common mathematical symbols, by the way, in physics that we use for angles, phi and theta. So I've labeled that angle in the upper right phi. But cosine, now look at the three trig functions, cosine, sine, tangent, but now for phi. But cosine is still length of adjacent over length of hypotenuse, that's its definition. But given phi, adjacent means B, and hypotenuse means C. So for the angle phi, cosine phi is B over C. Sine still means opposite over hypotenuse. But for the angle phi, opposite means the length A over hypotenuse length C. So for phi, sine phi is A over C. Tangent phi is, by definition, sine phi over cosine phi. And in this case, that turns out to be A over B. But that's the same as the length of opposite over adjacent. Okay, so we've defined sine, cosine, and tangent. Now, of course, we remember, I suspect, our old friend Pythagoras. Pythagoras, who taught us a long time ago that for a right triangle, there's a nice simple relationship between the lengths of the three sides of the triangle. The length of one leg squared plus the length of the other leg squared equals the length of the hypotenuse squared. In this case, a squared plus b squared equals c squared. We all know that. What if we take the Pythagorean theorem result and just divide both sides of the equation by the length c squared? As long as you do the same thing to both sides of an equality, you maintain an equality. So if I do that, I get this expression right here. A over c quantity squared plus b over c quantity squared equals 1. Oh, but wait a minute. For the angle theta, a over c is cosine of theta. B over c is sine of theta. So that expression I just wrote is equivalent to cosine squared theta plus sine squared theta equals 1. Or what if I use the other acute angle in the triangle, phi? Then a over c is sine phi, and b over c is cosine phi. So then Pythagoras basically says sine squared phi plus cosine squared phi equals 1. Well, this is the most important, what's called trig identity. Okay? This is called a trig identity. And I'll put an exclamation mark. It's the most important one. Probably the first one you were taught in a trig class, first trig identity. Sine squared of an angle plus cosine squared of an angle equals 1. Or cosine squared plus sine squared equals 1. It doesn't matter which one goes first. You take an angle, you take the sine of it, you take the cosine of it, you square them and you add them, and you're always going to get 1. We will use that identity a lot. Now I have some other identities, which we'll use less frequently, but every once in a while. So I've listed them here and put boxes around them. There's the so-called double angle identities. There's the so-called law of cosines and the law of sines. I've listed them here because you might find them useful. But what I really want you to take away from this slide are the definition of sine, cosine, tangent. Be able to work with either acute angle in a right triangle and work with sine, cosine, or tangent. And the trig identity, sine squared plus cosine squared equals 1. Now, another thing you need to be able to recognize when you see them are plots of the functions sine, cosine, and tangent. Okay? All right, so here I have all three plotted. I've taken this out of your book. The first plot is really sine theta on the y-axis and theta on the horizontal axis. For theta between 0 and 360, although it also shows negative angles, doesn't it? We better talk about that for a minute. Look at the picture down here in the lower left. I've drawn an xy coordinate system, and I've just drawn a line coming out from the origin. You could think of that as being the direction of a vector. I could even put a little arrowhead on it. Then the direction of that vector would be denoted by the angle theta between that vector and the plus x-axis. Okay, now for the first vector I've drawn, the one in the first quadrant, the angle you can see, you naturally go from the plus x-axis and you go up counterclockwise to denote your angle. By definition, counterclockwise angles are positive. But what if the vector I was talking about pointed from the origin down this way, so the arrowhead goes like that? Then when you measure the angle, one convenient choice, start from plus x and go this way, right? Until you get to the vector. Then you had to go clockwise to get to the vector. Clockwise angles, theta, are negative. So we will come across negative angles, because sometimes it's convenient to go clockwise and not counterclockwise. That's why this graph of these trig functions shows some negative angles. Okay, so the first graph is sine theta versus theta. You need to be able to see this graph, this first one, and recognize it. Oh, that's the plot of sine. Sine theta versus theta. Notice it starts when theta is 0, sine of 0 is 0, so it starts at 0, and then it rises up. At 90 degrees, it's got its maximum of 1, and then it starts to come down. At 180 degrees, the sine of 180 is 0. Beyond that, it goes into negative territory. The sine of 270 is negative 1, and back around to 360, it's 0 again. Sine function. Okay? All right. Next is the cosine function. So the second graph is cosine theta on the vertical axis and theta on the horizontal. And now you see the cosine function, and you need to be able to see that plot and recognize it as a cosine. So now we see at theta equals 0, cosine of 0 is plus 1. And then it goes down by the time we're at 90. The cosine is 0. When we're at 180, the cosine is negative 1. When we're at 270, the cosine is 0. And at 360, we're back to plus 1 like we were. Okay, that's cosine. The third graph is tangent theta versus theta. It's a little bit more interesting, perhaps, you might say, than sine and cosine, but you need to be able to recognize that graph when you see it. So when theta is 0, tangent is 0. As you approach theta of 90, the tangent function becomes more and more positive and bigger. In fact, it diverges. That's called a vertical asymptote there at 90. Tangent of 90 is undefined. You go beyond 90 and you cross over to large and negative. By the time you get up to 180, the tangent is 0 again. At 270 degrees, you have another vertical asymptote. And then it crosses through and becomes negative, and 360 at 0 again. Okay, so that's tangent theta with vertical asymptotes included. And again, you need to be able to recognize those graphs or sketch them yourself, pretty much from memory, when presented with them or asked to draw them. Now I want to say one more idea about these graphs, because it's somewhat important. Not somewhat important, it is important. What if I tell you that I have an angle theta such that the sine of it, sine of theta, is 1/2, 0.5. In that case, what we're likely to ask is, what's the theta? What is the angle theta if the sine of it is 1/2? The way you answer that mathematically is you do an operation to both sides, namely you take what's called the inverse sine, written like that. You take the inverse sine of the left, sine theta, and the inverse sine of the right, inverse sine of 0.5. And because the operation sine and inverse sine are mathematical inverses, on the left, inverse sine operating on sine undo each other, and you're just left with theta. And on the right, then you are left to calculate the inverse sine of 0.5. Now the good news is we have calculators and computer programs that are programmed to calculate inverse trig function values. So all you have to do is go to your calculator, make sure it's in what's called degree mode, if you want the angle in degrees, and have it give you the inverse sine of 0.5. If your calculator is in degree mode, you will find that it gives you a result of 30 degrees. So we say that the inverse sine of 1/2 is 30 degrees. You can see that, perhaps, if we look on our plot of sine theta versus theta. Let's first sketch where 1/2 would be on the sine axis, right about there. Go over to the graph, and then come down. That should be about 30 degrees on the theta axis. And that is what your calculator will give you when you ask it for the inverse sine of 1/2, 30 degrees. However, here's a subtlety to be aware of. Look at this graph of sine theta. If I tell you that sine theta is 1/2, so that you're right here, on the vertical axis, there is more than one answer for theta. There's more than one theta whose sine equals 1/2. All you got to do is go across until you hit the curve again, right there, and then go down. And right there is another theta whose sine equals 1/2. That angle happens to be 150 degrees, by the way. But your calculator won't give you that answer. And yet there may be a physics problem situation where it's the 150 that's the correct answer. Just be aware then that your calculator won't give you that. It'll say 30. But you can see from the graph of sine that 30 isn't the only possible angle. In fact, there are more than just 30 and 150. You could draw the sine on and on. You just got to be aware of that whenever you do calculate an inverse trig function value. That there can be more than one answer, but your calculator will only give you one answer. In fact, if you look carefully at this graph, you'll see there's part of the curve, that's a little bit darker than the rest. See that there? That's the part that the calculators are programmed to give you. Okay? Sorry about that. That's the part that the calculator is programmed to give you, an angle between, in this case, -90 and 90. So again, if you do inverse sine of 0.5 in your calculator, it'll give 30. Because that's the region it's programmed to give you an answer in. But the correct physical answer might be 150. You can only tell from the context of the problem. Similar kind of thinking applies to the cosine graph or the tangent graph. What if I tell you that cosine theta equals 0.5? What's theta? So let's go to 0.5 on the cosine theta axis, roughly. Go over till we get the curve, and then come down. You can see it's going to be a bigger angle than it was for sine. You take the inverse cosine of 0.5 with your calculator in degree mode, you'll find it's 60 degrees. But you can see that's not the only possible answer. I could instead go over this way and hit the curve and go down. Then the answer would be negative 60 degrees. The calculator, however, will only give me positive 60. It might be, in some cases, that negative 60 is correct. You'll only know from the context of the problem. The dark green part of the curve shows you that part of the theta axis that a calculator is programmed to give you for your inverse trig, inverse cosine. It's only going to give you an answer when you do inverse cosine that's an angle between 0 and 180. And you can do similar kind of thinking with the tangent function. So I'll let you think about what might be the possible answers for theta if I told you that tan theta equals 0.5. Okay? All right, so that's our review of trig. Now with that in mind, I come to one of the most important slides in the whole chapter. Okay? Finding the scalar components of a vector. So here's the task. I put a star by it because it is vital that we be able to do this. In this approach, we're going to imagine that we've been given two things, the magnitude and the direction of a vector. I'll denote the vector symbolically as A arrow. So we've been given its magnitude, A arrow absolute value, and its direction, denoted by an angle theta, measured from the plus x direction. With those two pieces of information, magnitude and direction, we are to find the vectors, what are called scalar components. And we have to do this for any vector in 2 dimensions. All right, so let me start talking about the pictures that you see here. Let's start over here in the left. Here's our vector. I've drawn it as an arrow with a certain magnitude and direction. It happens to have been drawn so that the arrow itself is lying in what you would call the first quadrant of the xy coordinate system. But there it is, A arrow, and it's got some direction theta, measured from plus x. That direction right there is plus x. That's the direction. Okay, here are the scalar components. They are the projections of the arrow, the vector, along the coordinate axes. So for example, if you project the vector A onto the x-axis, then you drop perpendicular lines straight down from the tail and from the head until you hit the x-axis. And then you draw a little arrow with an arrowhead along the x-axis. The arrowhead on that arrow I just drew is determined by the arrowhead on the original vector. And that is the projection of the vector onto the x-axis. That's the scalar component along the x direction, and it is denoted A subscript x. It's the x scalar component of the vector A. I will just tell you, by the way, most people will just say it's the x component of the vector A. Now we can do another scalar projection of the vector A now onto the y-axis. So now you draw perpendicular from the tail of A to the y-axis and from the head of A to the y-axis, and you draw an arrow with an arrowhead along y. And that represents the projection of A along the y-axis. And that's called the y scalar component, a sub y. Okay? All right, that's just a picture showing you what we mean when we talk about the scalar components of a vector. We mean the projections of the actual vector, the arrow, onto the respective axes. There's nothing sacred about where I drew this vector A. I drew it in the first quadrant, but I could have drawn an arrow with the same magnitude and direction, but lying in the second quadrant. That's the second picture here. And I can then still draw the projections along the x and y directions, and I'll get the same projections. If it's the same magnitude and the same direction, then that's all you have to know. Doesn't matter where you actually draw the arrows. So this picture here in the middle, although it looks very different from this picture on the left, is really no different at all, and shows the projections of the vector onto the x and y axes, and therefore the scalar components, a sub x and a sub y. And those components, a sub x and a sub y, are the same in both pictures. In fact, big arrow now pointing to the right, the picture on the right is the kind of picture you're going to see me draw the most. So let me get rid of all this extraneous stuff. Okay? The picture here on the right is the one we're going to draw the most. And here's how I like to think of the vectors, and I think you should do the same. I have the original vector with a certain magnitude and direction, a arrow. And I've now represented the projections, the scalar components, a sub x and a sub y, also. But I've drawn a sub x, a sub y, and a arrow so that they are lined up in a way that makes a right triangle, where the components, a sub x and a sub y, here and here, are the legs of the right triangle. And the vector itself, here, is the hypotenuse. And that is a very handy diagram for relating the vector and its two components. And I'm going to draw that kind of picture pretty much all the time when I have to figure out the components, the scalar components of a vector. Let me point out one other thing about how we're drawing arrows here, because it's a detail that often gets overlooked. The vector itself, the actual vector, symbolically a arrow, graphically the arrow itself. The way your book draws an actual vector is it draws a line, and the arrowhead, the tip of it is open. See that right there? Or I'll draw it down here. Line with an open tip, arrowhead. That's what they mean by a vector. Scalar components are still kind of directed lines, so they have arrowheads on them, but they're simple arrowheads, like that, and that. So when we draw simple arrowheads, we're just talking about the components of the vector. And the arrowhead on the components is really just telling you whether that component is a positive number or a negative number, as we'll see. But the vector itself is always drawn as a line with an open tip arrowhead. Okay, now, last thing I want to do is look at an animation that shows a vector. And let's see. Okay, so now, get this configured so that you can see it. I have an animation showing you an XY coordinate system with X in meters and Y in meters, and a vector A arrow, that you can see right here in the middle. And it's got a certain magnitude, in this case 4. The units here are incorrect. I'm sorry, that hasn't been corrected, but of course they would be meters. So this vector has a magnitude of 4 meters. And its direction is denoted by the angle theta. See the red arc down here, measured from plus x? And right now that's set at 30 degrees. Okay. I want us to go through calculating the scalar components of that vector, okay, given the information magnitude and direction. All right, to do that, I go back to my tablet, get a new screen, and start drawing some pictures for you. All right, let me draw the x-axis, the y-axis. Now let me draw the vector A. I'll draw it in red. It's drawn coming up from the origin. It's got a certain magnitude and a certain direction. We know the magnitude. Notice how I denote it. A arrow absolute value is 4 meters. And the angle theta, notice it's measured counterclockwise from plus x, so it's a positive angle, is 30 degrees. I want to sketch on this diagram the two components, a sub x and a sub y, and then calculate their numerical value. Use purple for the components. You end up just drawing a right triangle. The vector is the hypotenuse, the components are the legs. Okay? But put little arrowheads on the components based upon the arrowhead of the original vector. So I'll just drop perpendicular down like that. That'll help me visualize. Start here and go across like so. That's a sub x. It's the projection of A along the x direction. And then draw over here a regular arrow, but it's got to point up to go to the tip there of A. That's a sub y. Now I've created a little component triangle. And I'm just going to use trig to find ax and ay. Okay? In other words, what's the numerical value for a sub x and the numerical value of a sub y? What are the scalar components, a sub x and a sub y? This is where we use the right triangle trigonometry and definitions of sine and cosine. All right, let's just think about this a minute. This is really important, what I'm about to say next. What I want is that side right there. I want a sub x. Let's start with that, right? That side, notice, is adjacent to the angle theta. One of the things I know is the length of the hypotenuse, because that's the magnitude of the entire vector. That's 4 meters. I also know the angle theta, 30 degrees. So I know the length of the hypotenuse, the angle theta, and I want the length of the side adjacent to theta. This is where I remember cosine of an angle, theta, is adjacent over hypotenuse. Or, rearranging, the adjacent side is equal to the hypotenuse times the cosine of theta. And the adjacent side is a sub x. And the hypotenuse is the magnitude of A. So A sub x is equal to hypotenuse, magnitude of A, cosine theta. And the magnitude of A, 4 meters. And then I'm taking the cosine theta, which is 30 degrees. When you go to your calculator and have it give you the cosine of 30 degrees, make sure your calculator is in degree mode, it will tell you, to 3 sig figs, that the cosine of 30 degrees is 0.866. So I'm multiplying 0.866 with 4. I'm going to get a positive result. I get 3.46 meters. And the positive value for a sub x is consistent with the fact that the arrow on it points in the plus x direction. Now, if cosine theta is adjacent over hypotenuse, we know that sine theta is the length of the opposite side over the hypotenuse. Why do I say that? Because now I turn to a sub y, which is right here, and that side is opposite to the theta. So to get a sub y, I do magnitude A, hypotenuse, sine of theta. 4 meters is the magnitude of A sine of 30 degrees. You put that in your calculator. Make sure, again, your calculator is in degree mode. And it will tell you that the sine of 30 degrees is 0.5, 1/2. 0.5 times 4 is positive 2 meters. I get another positive value. That's consistent with the fact that the arrowhead on A sub y points in the plus y direction. Okay, well, we have just calculated the x and y scalar components of a vector pointing up into the first quadrant. Okay, now I want to change the vector a little bit. So now I go back to the animation, and I can change the angle of it with this slider or with this drop down. I'm going to put in an angle of 150 degrees, positive 150. That means 150 degrees counterclockwise from the x-axis. There it is. There's the new vector. Notice it points into the second quadrant. And you can see how that animation has drawn the x and y scalar components. I'm going to draw my own picture now of that situation and have us calculate the components. All right, back to the screen here. All right, let me draw XY coordinate system right here. I'm going to draw it a little bit different. Like that. And now let me draw the vector A. It points like this. Points into the second quadrant. All right, now we have to be able to draw the components. I like to make the right triangle, where the vector itself is always the hypotenuse and the components are the legs. I always start at the tail of the vector. I tend to go along x first, but in this case I have to go in the negative x direction. Let me drop a perpendicular down to the x-axis for visual reference. So I start at the tail of A, and I have to go out in the negative x direction, put an arrowhead on it. That's A sub x. Then I go along y to finish off the right triangle, put an arrowhead on it. That's A sub y. But now let's label angles very carefully. The angle theta that I said was 150 is measured from plus x counterclockwise. So I'm going to denote it by that. Okay, so in this case I'm using the symbol theta to be, actually, you know what I'm going to do? Sorry, folks. Let me change this to 100. I want to use 135 for reasons I won't go into it, but there, okay? All right. So, sorry, I want this angle to be 135. Okay, there, that's fine. So now let's just use the same formula I did in the first example to get AX and AY. We can do that. AX is magnitude A cosine theta, and AY is magnitude A sine theta. You can always do that to find AX and AY. Magnitude A cosine theta, magnitude A sine theta for AX and AY, respectively. But beware, I warn you, that if you use that approach, the theta has to be measured from plus x, like I'm doing in this picture you see right now. Okay? It must be measured from plus x. So doing that, we have magnitude of A, 4 meters, cosine theta, 135 degrees. Now you go to your calculator, you put it, make sure it's in degree mode, and you ask it, hey, what's the cosine of 135 degrees? It will say, at least to 3 sig figs, oh, negative 0.707. Negative. It will give you a negative result. You multiply negative 0.707 by 4 meters, and you get negative 2.83 meters. You have a negative x component. That, in fact, is consistent with this arrowhead on AX, yes? Because it points in the negative x direction. This negative sign right here on the x component is absolutely vital. And if not included, will give incorrect answers everywhere else in the problem. It's really important that you understand that. Now for a sub y, I do magnitude A, 4 meters, sine of, same theta, sine of 135 degrees. And you go to your calculator and you say, hey, calculator, what's the sine of 135 degrees? And it will say, oh, no problem, positive 0.707. Not negative, positive. You say, okay, thank you. 0.707 times 4 meters gives me positive 2.83 meters. That's consistent with the arrowhead on a y pointing in the plus y direction. And that plus sign for AY is very important. Okay? For this vector, the x component is a negative number, and the y component, scalar component, is a positive number, which the little diagram, the right triangle, shows you pretty clearly. Now I want to show you one other way to find the components in this case. In fact, it's the way I'm going to do most often, but I want you to be aware of the first way I just showed you. What if you have a situation where the vector doesn't lie in quadrant 1, quadrant 2, 3, or 4? We have quadrant 2. I'm going to now find the components using just the right triangle. So let me mark an acute angle. I'll do a double-headed arrow because I just want the size of this angle right down there in the lower right corner. And I'm going to call that angle phi, Greek letter phi. And I know from trigonometry, or actually geometry, that if theta is 135, that theta plus phi, just look at the picture, must be 180. So phi must be 180 minus 35. So phi is 45 degrees, that angle phi. I can use the little right triangle here in the picture and the angle phi to get AX and AY. That way I don't ever have to use an angle greater than 90. If you just want to avoid any complications associated with that. However, I'm going to show you the subtlety that you have to be aware of here. Let's start with AX using this second method. But I'm going to use the angle phi, not theta, to get AX. So now I note that AX is adjacent to phi, and I know the length of the hypotenuse. So I'm still going to use cosine. Cosine is length of adjacent over length of hypotenuse. Okay? And I'm going to just take length of hypotenuse times cosine phi. So length of hypotenuse cosine phi. So far it looks like what I did up above. However, the phi I'm going to put in here is 45 degrees. The cosine of that is not going to be negative, but I know already that the a sub x is negative here. When you use this approach with this angle phi like this, you have to put the negative sign in for that x component by hand. But it's not hard to see that you have to do that because you can see from your little diagram that a sub x is negative because of the arrowhead on a sub x pointing in the negative x direction. But the point is that if you use angles less than 90, like the phi in this picture, you're going to have to be able to see from your diagram which components are negative and put the negative sign in by hand. So this is negative magnitude A, 4 meters, times cosine of phi, 45 degrees. Not 135, 45. And you go to your calculator and you say, hey, calculator, what's the cosine of 45? And it will say, oh, that's easy, positive 0.707. So you multiply all this out, remember the negative sign you put in by hand, and you get negative 0.283 meters. Same x component we had in the first calculation. Of course, it had to be. Right? And then now, how about the expression for AY? Well, that would be length of hypotenuse sine of phi. And you have to decide for yourself and put in by hand whether it's positive or negative. And this one's positive, right? Because your diagram shows you that the a sub y arrow points up plus y. But you have to realize that yourself. The sign is positive. So that's positive 4 meters times the sine of phi, which is 45 degrees. And you can check with your calculator, but the sine of 45 is equal to the cosine of 45.707. But this one's now going to be positive. You get plus 2.83 meters, like we did in the first method. Okay, so whenever you have a situation like below that green line with a vector in either quadrants 2, 3, or 4, anything but quadrant 1, 2, 3, or 4, you have two possible ways to calculate the components. You can use the angle theta, measured from plus x, and use this first method right here that I showed you. Or you can take your little right triangle drawing, work only with an acute angle, like the angle phi that I showed you, and then put in the appropriate plus or minus signs by hand. And because of the various ways that we draw diagrams in physics, I'm going to tend to use this second option the most, because this little right triangle is going to be a really common thing for us to draw. But for now, the main thing is you need to practice so that you can become very comfortable calculating the scalar components of any two-dimensional vector given its magnitude and direction, no matter whether it's in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. And we're going to spend time in class practicing with that, and you're going to have homework problems to do that. Okay, but that's all for this video.